We can't imagine that now because we don't even get nominal returns on most things of 5-6%. But imagine a world where inflation is 5-6%. You got to make that just to stand still. Just to stand still, just to have the same purchasing power. So inflation, looking at your real returns, is a very real thing you have to do. And finally, leveraged returns. And we can gain leverage either by the use of derivatives or by the use of margin. That means our gains can be magnified, but so are our losses. And we must also account for margin loan interest. So when we're looking at leveraged returns, we've seen this before in corporate finance, where we looked at the idea of financial leverage versus operational leverage. Same concepts apply here. So let's look at an example of something here. I had this up before. We've already been through this. We calculated the holding period return for this particular scenario at 42.35. We found an arithmetic mean of 7.6% and a geometric mean return of 7.3%. So let's do something here. Let's say that our tax rate is 20%. We have an inflation rate of 2%. And let's calculate our real after-tax return for year 5, just for year 5, our real after-tax return. Well, we have a nominal return of 3%. So our after-tax return, now taxes are off our nominal amount. So we can take our 0.03 and we can multiply it by 0.8 because our tax rate is 20%. That'll be our nominal after-tax return, our nominal return. So what we want to do now is we need to discount that backwards by the rate of inflation. Because at the end of the year, we would have had a 3% times the 0.8 or 2.4%. So we would have had 1 plus 0.24%. And if we discount that back by at the rate of inflation, 1.02, and of course subtract our 1 after that, we will get 0.0039 or 0.39%. 0.39%. So in year 3, our after-tax real return is 0.39%. So we can look at our nominal return of 3%. And compare that with the real after-tax return. This is what we really get. That's what we walk away with. That's the effect on our wealth, 0.39%. Look at the wide difference. Almost 90% of that nominal return is gone. Almost 90% of it is gone. Some of it went away in taxes. The rest went away in inflation. And we pay our tax on the nominal amount, not the real amount. It would be nice if we paid it on the real amount, but we pay it on the nominal amount, which means inflation hurts us even more because it raises our tax bill. 0.39 versus 3. Another calculate and interpret. These things come in pairs, right? Calculate and interpret the mean, variance, and covariance of asset returns based on historical data. Okay, well, let's go. And on these, a lot of this can get detailed, but it's a repeat. Remember, variance was a measure of the dispersion of the returns, and we measured it as square deviations. So mu is the population parameter. That's the population mean, and we take the observation and we take the difference between the observation and the population mean and we square it, and we sum all of these squared deviations and we divide by n. That'll give us the variance. But since we typically don't know the population parameters, we use sample statistics. So we will use a sample and find the mean from that sample. When we do, we lose a degree of freedom. So that's why our numerator drops to n minus 1, because now we're constrained. We can only choose n minus 1 observations freely. Since we've set a mean for the sample, the last one must be constrained to equal that mean. Then we take each observation minus the sample mean. Again, the numerator is just the squared deviations divided by n minus 1. We'll get a sample variance. The standard deviation is just the square root of the variance, which is just this term in the roots under the root sign. And again, it's this term up here under the root sign, just the square root of the variance. Well, let's move from the measure of risk of a single asset to the measure of risk of a family, a group of assets, a portfolio of assets. So for the variance of the portfolio of assets, we're going to need certain things. We're going to have to calculate the variance of each asset and the covariance of each asset with each other. So that once we're finished, we'll have variances and covariances, and the variances and covariances are additive. So this is how we arrive at the variance of each asset. In here, what do we have in here? We have squared deviations from the expected value. Squared deviations of the expected value. We got expected value through the use of probability, so we simply weight this deviation by its probability of occurrence. And so this is just a weighted average of the squared deviations. This will give us the variance of each asset. When we move over to the variance, the covariance of each asset with each other, all we're really doing is, instead of looking at squared deviations, we're multiplying across. They're just cross products to get the covariance of each one. And then we can combine these two together in one formula, the sum through I through n and j through n of the weightings, wi, wj. These are the two assets, the covariance between the two returns. If it's the same return we're looking at, if asset I and asset j are equal, so if I is 1 and j is 1, we're talking about the same asset. The weighting is just squared, and this covariance turns into a variance of R. So the portfolio variance is the sum of all the variances and all the covariances. So on the variance of the portfolio of assets, here's what we have. If we want to break out that formula we ended with on the last screen, it is nothing more than the sum of, these are the variances. Remember, if I and j were the same, our wi, wj would end up being wi squared times the variance plus the covariance. So here, we've just broken down that last formula, saying that the variance of the portfolio of assets is nothing more than all of the variances of the individual assets within the portfolio, plus all the covariances between them. And covariance Ri, Rj can also be arrived at by finding the standard deviation of I and the standard deviation of j, multiplying them together, and then multiplying them by the correlation. Further, if we know the covariance between Ri and Rj, and we know the standard deviation of asset I and j, we can always find the correlation, which we'll do shortly. So if we had a two-asset portfolio, what would it look like? Well, it would be the variance of the first asset multiplied by the weighting of its squared, plus the variance of the second asset multiplied by its weighting squared, plus here we have wi, wj. Now remember, we have a covariance. If we have two assets, A and B, we're going to calculate a covariance of A with B, and you're going to calculate a covariance of B with A, hence the 2. Because if we know the covariance of A with B, we know the reverse, so we'll just multiply it by 2. So 2, the weightings and the covariance are ij. Or you can use correlation in there. If you know the correlation between the two, but you don't know the covariance, you can use the correlation in there. And of course, to find the standard deviation, this is the variance. To find the standard deviation, you just take the square root of whatever it is that you get. All of this in here is just all of this up here. I'm going quick because this is a review. All of this is derived very definitely in these videos up here. Well, let's do a problem here. We have two assets up, the S&P 500 and the MSCI index, and we're going to create a portfolio of these two assets with this weighting, 80% into the S&P 500, 20% into the other. The expected returns on the two indices are shown along with their standard deviation, and we know the covariance between the two, 0.5%. So we're looking at finding the return on the portfolio and the variance on the portfolio. So let's just move ahead here. The return we know is just the weighted average of the two returns. So it would be W1, the return on the first one, plus we'll weight the second one this way. That's all, and we just plug in the numbers, right? 0.8 times 0.0993 plus 0.2 times 0.1820, and that will give us 0.1158, or if you like it this way better, 11.58%. That should be fairly straightforward for everyone. It's just a weighted average of the two returns. Great. Let's do the variance of the portfolio, and you'll recall that it was the weighting squared on the the variance of the first asset plus the weighting squared of the variance of the second asset plus 2 times weighting 1, weighting 2, multiplied by the covariance of R1, R2. There we go. We just have to plug in the numbers at that point. So the difficult part of the covariance is just getting it straight in your head what you're doing. And the more you write out, when you do problems, the more you write out the formula each time. It just becomes part of you. It just becomes second nature, and you don't have to think. And if you can do this part, well, the rest is easy. You just take the numbers and plug them in. At that point, we've got our answer as soon as we've got this, right? Because plugging things in is easy. Watch your fingers on that calculator. There are times I hit plus when I should be hitting multiply, and I get the wrong answer. So let's just see what we get here. We have 0.8, and let's remember these are squared now, right? And our variance over here was 0.1621, but remember that's squared, plus we have 0.2 squared, and our variance is 0.3311 squared plus 2, our W1, 0.8, our W2, 0.2, and our covariance, 0.005. There's another place you might run into trouble with problems, is you'll see a 0.5 and you won't count enough decimal places and you'll get a wrong answer. So let's be careful about that. Let's make sure that we are putting things in the right way. Calculating this, we'll get 0.01682 plus this will give us 0.00439 plus 0.00160. And if we add them all together, we will get 0.02281. The standard deviation then of the returns is just the square root of what we just got, 0.02281, which will give us 15.10%. There we go. That's the calculate. Let's do the next part, which is interpret. What have we got here? Well, let's just look at the S&P 500, and let's say that we were going to make an investment in the S&P 500, 100%. What would we experience? What are the characteristics of this asset? Well, remember, we can describe every financial asset in terms of two things, return and risk. Return 9.93, risk 16.21%. So we want to know, can we do better than that? And we can do better than that in one of three ways. The first way that we can do better is to achieve a higher return for the same risk. The second way we can do better is to get lower risk at the same level of return. And the third way is to double end this one, is to get higher return with lower risk. That would be sweet. Did we do that by adding this other index that has a very low covariance between the two? By adding this other index, did we achieve that result? Well, we got 11.58, or at least an anticipation of 11.58%, versus 9.93. So we got higher on the return, but it doesn't matter unless we got the same or lower risk. We can always get higher return by taking on higher risk. Well, we got 15.1. So we actually were able to do better on the return and lower our risk by combining two assets together. And to see why this makes a lot of sense, let's calculate the correlation between the two. And we can calculate the correlation because we know that the covariance between two assets, R1 and R2, is the correlation between the two multiplied by the standard deviation of each one, the products of the standard deviation. And we know all of these things except for the correlation. So we know that this side is 0.005, which would equal the correlation, and the first standard deviation is 0.1621, and our second standard deviation is 0.3311. So all we have to do is just collect the terms and divide through. So our correlation will equal 0.005 over, and if you multiply these two and divide through, you will have 0.05367 over here, which will be 0.093. We'll leave it at 0.093. And remember, correlations range from -1 all the way up to +1, with 0 being no relationship whatsoever, -1 being a perfect negative correlation. So this would, you can think of it as being long and short the same asset, and +1 being 100% correlation, in which case you've got exactly the same asset. This is 0.09, so it's almost no correlation whatsoever, or very, very small correlation with it. So the reason we can achieve this result is when we add assets to a portfolio that are less than perfectly correlated, we can always reduce our risk. We're going to see more of that as we get to learning objective, I believe, E, calculate and interpret portfolio standard deviation, and F, describe the effect on a portfolio's risk of investing in assets that are less than perfectly correlated. But it's good to see it now so that it's in your mind. So when we get there, you'll say, I have seen an application of that. So the takeaway here is that we were able to get a better return for lower risk by combining two assets that are less than perfectly correlated. If you can bring that away with you from this, you got it. Well, there's just a few housekeeping things left to do to clean up this learning objective, and that's to contrast expected return versus historical return. Historical return, we know, was based on actual results, was based on something we actually saw. Expected return is a forecast. And we know that our expected return is a function of three things. It's whatever the risk-free rate is, our expectation for inflation, and the expected risk premium that we want for that particular asset. We've already looked at the components of a nominal return in that sense. So our expected return is based on a forecast that we have for what we think inflation is going to be, what we think the risk premium is, and what the current risk-free rate is. And historical returns, well, they've already happened. That's it. As a practical matter, we often assume that the historical mean return is an adequate representation of expected return. So we don't go through the process of outlining all the possible outcomes, assigning probabilities to those, and remember, we work our way backwards in a probability tree to the first node to get an expected return. We don't really do that. We'll start with the historical mean return. That's number one, is you take the historical mean return, and then you ask yourself a question, a pretty important question. Is there any reason I should expect the next X amount of year period to be significantly different than the last X year period? So if you're taking a 15-year historical period as the basis for your historical returns, and you know we haven't really talked about this too much, we've given it kind of short shrift, but listen, if you're basing your returns your expected returns on historical data, you have to determine, well, how far back are you going? Am I just going to go back 10 years and use those results as my expected return and standard deviation? Am I going back 20 or 40 or 100 years? It matters, because you'll get different expected returns and different measures of variability, different measures of risk for those periods. So if you decide that, well, look, I'm going to look at the past 15 years and derive my expected return and standard deviation from the last 15, bravo. Now, do you expect the next 15 years to look like that? Or the next 5 years to look like that? And if there's some reason why you don't expect it to look like that, you might say, you know what I think is going to happen is I think that volatility will increase, or I think volatility will decrease in certain asset classes. You might then make adjustments to those historical numbers based on some subjective feel. That's perfectly plausible to do, and then you can run different scenarios to say, here's what the data says, but here's subjectively how I tweaked that data, and I come up with these numbers or these numbers. You're free to do that. Let's just, when you're looking at the historical data, keep in mind that you're making an assumption when you base your expected return on that the future will look like that. If you have reasons to believe that it won't, use the historical data as your starting point, then modify it for what you think will happen. Some of the other investment characteristics that you would look at on a particular asset class, if you doubt normality, you would say, well, let me check skewness and kurtosis. and see if they're well within the range. If they're way outside, then I can throw normality out. I need another type of probability distribution to base my assumptions on, or to base your analysis on, because the assumptions of normality fail. Skewness and kurtosis covered in video 25 for quant. I'll place that right after this video so that you can watch it. No point me covering it again when it was covered perfectly well, perfectly, a little pat on my back there. When it was covered just, it was covered well enough in video 25. Well, we're on a new learning objective. Keyword here is to explain. Explain risk aversion and its implications for portfolio selection. I think we have an idea of what risk aversion is, but let's say it formally so that we're aware of it. Let's say that we have two options. We have a sure thing that pays $25, and we have a gamble, which pays $50 or zero with 50-50 probability. So that the expected value, the expected return of this gamble is $25. In other words, they have the same expected payoff, but one has variability, the other has no variability. So the same payoff, one with lower risk, one with higher risk. So risk aversion says, take the sure thing. We either maximize our return for a given level of risk, which means if we have two investments that have the same level of risk, we'll take the one with the maximum return. Or, as this situation shows us, we can minimize the risk for a given level of return. Same return on each one, but this one has less risk. Now, you may say, well, it's not really the same return. Here, there is a chance of doubling your money. There is a chance, true. But on repeated trials, it would average out to $25 each time on repeated trials. This is $25 every time. You're not going into the market once, buying one stock, and then leaving and never showing up again. You're going to do it over and over and over and over again, so you better get used to the idea of an expected return as opposed to saying, yeah, but I could double my money. Sure, but on repeated trials, that's the idea behind expected value, right? So they have the same payoff, really, but this one has no variability. This one has wide variability. So think if you did this 100 times. If this is 50-50. If you did this 100 times, you would get, on average, $2,500 here. You would get $2,500 here, except no risk. That's the idea behind it. Risk-seeking. Take the gamble. You get satisfaction from the uncertainty. Now, I'm troubled by this risk-seeking thing. I've known a lot of traders. I haven't known a single one that points to risk first, says, this, well, look how risky this is. I'm going for that. I don't know anybody who places risk first and chases that thrill. Typically, they get in their head the idea of this big gain without paying attention to the risk. So that we have this idea of calling them risk-seeking when, in essence, they're sort of risk-ignorant. So I don't like the word risk-seeking. Somebody taking the gamble just doesn't understand the difference between risk and return and doesn't understand how to measure it. If they did understand it, they'd say, hey, you know what? You're right. Take the sure thing. So when I see risk seekers, I don't say, wow, they're really going for risk. I say, wow, they have no idea of the risk they're taking. So I don't like the word risk seeking. I like the word risk ignorant. Risk neutral. They're indifferent between them. And I can see that over repeated trials. I'll get 2,500. Here I'll get 2,500. Yeah, I don't care. Now here's the thing. Here's where I get really indifferent, and most of the finance literature will say you're absolutely right, and I think you'll find this yourself. If I don't have anything, I'm not indifferent. I want that sure thing because it matters to me. But if I'm a billionaire and somebody offers me, hey, do you want $25 or do you want to gamble? I don't care. Toss the coin. I don't care. Let's see what happens. Because I couldn't care less. It makes such a small amount compared to my wealth that I'm truly indifferent behind that. So when you see somebody taking a big risk, you can say, well, either it's such a small payoff to them they couldn't care less and, hey, may as well have some fun, or they just don't understand, right? So let's define risk tolerance for an investor. And since we've done the risk management reading, the previous to this one, we sort of have an idea what risk tolerance is, but we'll say it again. It's the level of risk willingly accepted to achieve our investment goals. If we have lower risk tolerance, that means the lower the acceptable level of risk we are willing to assume, and the higher our risk aversion. So the less risk averse we are, the more tolerant we are to risk. So let's combine that now with utility theory. Remember back in microeconomics, we talked about utility and how consumers try to maximize their utility by making choices between baskets of goods. Well, so we can think of investors doing the same thing. Now, before I go too far into this utility theory, before we get down to this formula down here, I want you to, first of all, put this in perspective. Can we describe a consumer's choices or an investor's choices by a deterministic function? No, we can't. We can't. So let's clear the air on that first. So why are we using math? Why are we using equations like this in curves and graphs? Here's why. Because we can say something in a sentence that is perfectly logical. And we've already said it in a sentence that's perfectly logical. Investors, for the most part, tend to be risk averse. By risk averse, we mean when given two investments with the same expected payoff, they'll choose the one with the lower risk. We can say that in a sentence, and most people would say, yes. The problem with that is if we want to say more complicated things, we have to use more sentences and longer paragraphs, and a lot can get lost in that. So that what we want to do is we want to say that in a nice little equation where we can read it and go, okay, I understand what you're saying. Here's the trap. The trap is in looking at these equations and thinking that that is what we're doing, that our outcomes are that deterministic, and they're not. When you see math talking about the tendencies of a human to behave a certain way, I want you to look at that equation and say, I'm going to turn that equation into words because the equation's really just standing in for the words. That's all. We're not really meant to buy into the equation. The equation's just an easier way to say the sentence. That's it. This is not a deterministic equation. This is a tendency. This is a pretty strong tendency. So if you think of it that way, we won't get wrapped up in saying, well, I don't know if you can describe human behavior with an equation. You're right, we can't. But we can use the language of math to talk about that tendency because that language is less prone to misunderstanding than words. All right, there we go. So let's go back to utility theory and these indifference curves. If you have forgotten this, you can go back to microeconomics and refresh yourself on that there. With utility theory, for microeconomics, we use the word consumers. Here we're going to use the word investors. Investors derive satisfaction or utility. They derive satisfaction from particular choices relative to others. So if we describe a risk-averse investor, which we already know what risk-averse means, it might look something like this, where we can measure some utility by, here is the expected return that they're expected to receive, and we are subtracting from that expected return for risk. You notice it's minus, don't worry about the 1/2 right now. Let's just not worry about that. Let's just worry about what we're saying here. Let's turn this into words. What we're saying is that we can take away from our utility with increased risk. So increased risk will take away from our satisfaction. That's what this is saying. Because we're risk averse. We tend to be risk averse. So if you increase the return and it increases the risk, well, there's a trade-off. It keeps me balanced. Now, what is this A factor in here? Well, this A factor brings this little formula down to the level of the individual, because A will be different for every individual. A is a measure of risk aversion. You may be more risk averse than I because you're 65 and I'm 25. So that I would be more risk tolerant than you because I got more time. I got a longer time horizon, right? So A is the marginal return required to accept additional risk. So the higher A is, notice that if this A gets bigger and bigger, this negative value gets bigger and bigger, which decreases our utility. So a small a, an A of 0, means that we have no risk aversion whatsoever. An A of 0, this whole term becomes 0, which means we're not concerned with risk. But as A starts to increase, we become more and more concerned with risk. So this brings it down to the level of the individual. So we'll rewrite our utility function at the top here, and we'll say some things about it. So this function assumes, number one, investors are generally risk averse, but do prefer more return to less. So it's not a matter of that we're going to focus on the word risk averse and say, well, if that were the case, all investors would hold risk-free assets. No, no, no. They're risk averse, but they prefer more return to less. And remember what risk averse says. Risk averse says given two investments with equal return, a risk-averse investor will choose the one with the lowest risk. That makes perfect sense. So we say investors are generally risk-averse. This is a tendency to behave in a certain way that makes sense when you say it in a sentence. Investors are able to rank different portfolios based on their preferences. Now, you may stop here and say, wait a minute, I know some pretty stupid people. They can't do that. They don't even know what risk they're taking on. And besides, I said it earlier that I've seen some cowboys out there taking risk. I don't say they're risk-seeking. I say they're risk-ignorant. Are they able to rank their portfolios based on their preferences? Well, here's the deal. They don't have to be. This kind of assumption means that as long as there is a significantly a large amount of investors that represent a significant amount of money, then it holds in the marketplace. It doesn't have to hold for every little individual. Just as long as more, on average, can do that than not. And I think most can. I think if you look at two different stocks and you pull up a chart and some history on the stock and start looking at the price movement on the chart, look at the fundamentals, combine the two together, most people could say, well, I prefer this over that. They know what they like. Preferences are internally consistent. And now again,